Chapter 15, Number 69. During a thunderstorm, winds with a speed of 47.7 meters per second blow across a flat roof with an area of 668 meters squared. A. Find the magnitude of the forces exerted on the roof as a result of this wind. And B. Is the force exerted on the roof in the upward or downward direction? Explain. So let's draw a little picture. What we have here is some building where there's a flat roof and there's a velocity 2 of 47.7 meters per second, and we assume that inside the house there's essentially no air motion. True or not? Well, probably pretty close to true. Certainly not 50 meters per second worth of air motion. So we're going to use Bernoulli's equation, and we're going to say, given that there are two different pressures, there's the pressure inside the house and pressure outside of the house, we would have Bernoulli's equation will tell us that the pressure plus 1/2 rho V1 squared is going to be the same as pressure outside plus 1/2 rho V2 squared. And here we really are talking on either side of the roof, and so the height doesn't change very much, so I can again neglect the height difference, the rho G Y term in here. And so we can say, what is the magnitude of the force exerted on the roof? Well, the magnitude of the force exerted is going to be, if we think of the roof as its own little free body diagram, there's going to be a force from below, which is coming from pressure 1, but there's going to be a force from above, which is coming from pressure 2. And what we want is the combination of these, which would be F1 minus F2. If that turns out to be positive, then we have an upward force, and if it turns out to be negative, we have a downward force. But this, of course, is going to be P1 times the area, and the other is going to be P2 times the area, because that's what pressure means. So I can pull out this and say that my force is the difference of pressures times the area. And if I go back up to here, I can say, well, bringing P2 over and then bringing everybody to the other side to make it work, we get that P1 minus P2 is going to be 1/2 rho V2 square minus 1/2 rho V1 square. So the difference in forces ends up being 1/2 rho V2 square minus 1/2 rho V1 squared, all times the area. Gonna clean this up a little bit by factoring out everybody who's a common factor. So 1/2 rho A, and then we have V2 square minus V1 square. Oh, but look, V1 is 0, right? It's at rest inside. So I can put that to be 0, so that actually kind of goes away completely. And I'm left with that the difference in forces is 1/2 rho A times V2 square. So I can just put in some numbers and figure out what they come out to be. Notice it will be a positive number. The net force will be upward. We're going to use the standard density of air as 1.29 kilograms per meter cubed. Is that exactly true? Yeah, probably not quite, but probably enough. And we don't have any information to go around it, so we'll say that that's fine. And then we have the area, and then we were given the 47.7 meters per second quantity squared, and we end up with a number of 980,331 newtons. Now, if we look up here, we have 3 sig fig there and 3 sig fig there, and we have the density of 3 sig figs, so we should only have 3 sig figs down here, and so we end up with 980 times 1,000 newtons, or 980 kilonewtons.